Today we're going to move on to the second part of Chapter 3, Section 2. We're still talking about linear functions, and we're going to look at the graphs of them and graphing them ourselves a little bit today. So let's get started. This is just a representation of functions, just a little concept summary. This is just different ways you can represent a function. So you can represent it with a phrase or words, and output is 3 more than the input. That can be translated to an equation. Y would be our output, so our output is 3 more than our input. X is the input. So that would be our equation for that phrase. And then that can be translated to an input-output table, or just a table of values. If I plug -1 in for X, -1 plus 3 gives me 2, so my Y value would be 2. Plug 0 in for X, 0 plus 3 is 3, so my Y value is 3. So on and so forth. 1 plus 3 is 4, 2 plus 3 is 5. Our input-output table can translate to our mapping. -1 maps to 2, 0 to 3, 1 to 4, and 2 to 5. And then all of that can translate to our graph over here. It's just a line graphed on our graph, connected with a line through it. So that's just multiple ways to represent a function. So let's talk about graphing linear functions. A solution of a linear equation in 2 variables is an ordered pair. We've all dealt with ordered pairs before. That makes the equation true. The graph of a linear equation in 2 variables is the set of points, or ordered pairs, in a coordinate plane that represents all solutions of the equation. Sometimes the points are distinct, other times the points are connected. So if I have a graph of a line, all that line means is that every ordered pair on this line is a solution to that equation we were dealing with. Every single one. So there's an infinite number of solutions or ordered pairs that make the equation true. So that line just represents all the ordered pairs that are solutions of the equation. So let's talk about the domains of these graphs that we're going to be graphing today. We've talked about a discrete function and a continuous function. The discrete function was not connected. The continuous function had all the points connected. So in a discrete domain, that is a set of input values that consist of only certain numbers in an interval. So similar to our discrete function, but we're just talking about the domain here, the set of x values. So here's a little example they gave. All the integers from 1 to 5. Well, integers are a very specific set of numbers, and so we can only do the numbers 1, 2, 3, 4, and 5 on that interval, because 1.5 is not an integer. Any decimal, any fraction would not be an integer. So it's a very specific set, so I can only use 5 ordered pairs there. A continuous domain is a set of input values that consist of all numbers in an interval. So all numbers from 1 to 5, that can be any number. That could be 1.999756521. That would be on my continuous domain. But it still includes all those integers because those are still numbers within that range. So this would just be all the numbers on this line on our graph. No matter if it's a decimal, fraction, whatever, it's a part of that continuous domain. So once again, the discrete domain is a set of input values that consists of only certain numbers in an interval. Continuous domain is a set of input values that consist of all numbers in an interval. So let's look at this example 4 from our book. The linear function y equals 15.95x represents the cost y in dollars of X tickets for a museum. Each customer can buy a maximum of 4 tickets. So it wants us to do 2 things on this example. It wants us to find the domain of the function and then tell if it's discrete or continuous and explain. And then it wants us to graph the function using its domain. So, I need to first find the domain of the function. So, since we're talking about tickets to a museum here, I want you to ask yourself, can I buy part of a ticket? Can I buy half of a ticket or a quarter of a ticket? If you think about that really hard, the answer is no. You either buy a ticket or you don't. Or you buy 2 tickets or you buy 3 tickets, so on and so forth. So, but it also says that each customer can buy a maximum of 4 tickets. So you can either buy 0 tickets, 1 ticket, 2 tickets, 3 tickets, or 4 tickets. You can only buy 0, 1, 2, 3, or 4 tickets. Like I said, you can't buy any other number because you can't buy part of a ticket. So this would be my domain right here. My domain is 0, 1, 2, 3, and 4. So since this is only certain numbers on an interval, then this must be a discrete domain. So I'd say it's a discrete domain because you can only buy a certain number of tickets. So that helps me understand that I'm only using certain numbers on that interval 0 to 4. So domain 0, 1, 2, 3, and 4. It's a discrete domain because you're only using certain numbers on that set. So there's letter A. Now we need to find letter B. It says graph the function using its domain. So I'm going to erase letter A. Give myself a little more room to work with letter B. Letter B, it says graph the function using its domain. So domain was 0, 1, 2, 3, 4. We need to keep in mind that my domain is my set of x values. So in order to graph my function, I need x values and I need y values to create ordered pairs to be able to graph them on a graph. So I'm just going to use the table of values. My x values are 0, 1, that's not going to give me enough room. Zero, 1, 2, 3, 4. To find my y values, I can just plug my x values into my function. Y equals 15.95x. So for 0, I just do 15.95 times 0 instead of times x. Well, 15.95 times 0 would just give me 0, so that's my corresponding y value for that x value. I'm just going to do that with all my x values. Just plug them in to my function. So for 1, it would be 15.95. Because 1 times 15.95 is 15.95. Plugging 2 in. That would give me 31.90. Plugging 3 in. would give me 47.85. And plugging 4 in, would give me 63.80. So now I'm going to use this table of values to graph all of my ordered pairs. My ordered pairs are 0, 0, 1, 15.95, so on and so forth. So I have my table of values over here with my graph. And if you notice, I made my I actually made the wrong axis go up by tens. I need to make my y-axis go up by tens and not my x-axis. My apologies. That's better. I made my y-axis go up by tens because my y values are getting so big so quick. So, my first ordered pair is 0, 0. So I put a point at the origin. 0, 0. Next ordered pair is 1, 15.95. So I'm going to go right 1, up 15.95, which would be right about there. Next ordered pair is 2, 31.90. I'm going to go right 2, up 31.90. Would be right about there. 3, 47.85, right 3, up 47.85. Right about there. And then right 4, up 63.80. Right 4, up 63.80. Be right about there. So there's my graph of my function that I was just looking at. Now, if you notice, we do not connect the dots on this graph. The reasoning behind that is because this has a discrete domain. Only certain ordered pairs, certain x values are a part of the domain. I don't want all the numbers between all those x values. I just want those certain x values with their y values. So for a discrete function, discrete domain, we're not connecting the points on our graph. So hopefully that makes sense. If it's discrete, you're not connecting the points. If it's continuous, you would connect the points. So I have answered everything I need to answer for example 4. Let's move on to another example, example 5. It says a cereal bar contains 130 calories. The number C of calories consumed is a function of the number B of bars eaten. It says, does this situation represent a linear function? Explain. Find the domain of the function. Is the domain discrete or continuous? Explain. And then graph the function using its domain. So, the letter A is asking, does this situation represent a linear function? So we need to look at our x and y values, or in our case, our b and our c values. So, it says for every bar eaten, the number c of calories consumed goes up. So, if I eat 1 bar, the number of calories I've consumed is 130. If I eat 2 bars, the number of calories I've eaten is 260. 3 bars would be 390, so on and so forth. So as we saw yesterday, I want my x value to increase by the same thing each time, my y value to increase by the same thing each time for it to be a linear function. Well, here, my x value is increasing by 1. At the same time, my c value is increasing by 130. So this would be a constant rate of change, so we would say, yes, this is a linear function because the rate of change is constant. So letter A. It is a linear function because the rate of change is constant. Hope you all see how we broke that down. Because like I said, as B increases by 1, as I eat 1 more bar, the number of calories I've consumed increases by 130. So that's just increasing at a constant rate. Okay, letter B. It says find the domain of the function. Is the domain discrete or continuous? Explain. So earlier we were talking about museum tickets. We couldn't buy just part of a museum ticket. We had to buy 1 museum ticket, 2 museum tickets, 3, so on and so forth. If we're talking about a cereal bar, you can very well eat part of a cereal bar. You can eat as much of the cereal bar as you want. You can eat part of it, all of it, half of it, 3/4 of it. You can eat any part of it that you want. So, the number B of bars eaten can be any value that's greater than 0. It can be 1.5, it could be 1, it could be 0.5, anything that's greater than 0. So, this would be a continuous function, and so the domain would also be continuous. So the domain would be the number of bars I've eaten can be greater than or equal to 0. I can eat 0 bars, or I can eat anything that's greater than 0. So this would be my domain, actually. So my domain equals set of all real numbers b, such that b is greater than or equal to 0. There'd be my domain. And like we said, since it can be any number that's greater than 0, it is continuous. So I'd say it is a continuous domain. So there's letter A, there's letter B. Now it says I need to graph the function using its domain. So I'm going to do something similar to what I did on the previous example. I'm going to make a table of values. And I'm going to use only whole numbers. So I'm going to use 0, 1, 2, 3, 4. And that should give me enough points on my graph to be able to create my line. So I've already kind of did this earlier when I was explaining that it was a linear function. If I eat 0 bars, I've eaten 0 calories. If I've eaten 1 bar, I've eaten 130 calories. 2 bars was 260. 3 bars was 390. And then 4 bars would be 520. So here's my table of values. It's giving me a bunch of ordered pairs that I can now graph. So now, like I said, I can graph my ordered pairs from my table of values. So let's go look at our graph. If you notice, I made my y values go up by 100s this time since the y values increase so dramatically. Sometimes you need to do that. Sometimes you need to change the numbers on your axes to match the situation and the numbers you're dealing with. So, I'm just going to graph these ordered pairs again. 0, 0. That'd be right at my origin. 1, 130. So I'm going to go right 1, up 130. Be right about there. 2, 260. Be about there. 3, 390. Go right about there. And 4, 520 would be about there. So there's my ordered pairs all graphed. Now in the previous example, we did not connect our points with a line because it was discrete. It was a discrete domain. Here we have a continuous domain, so I want to go ahead and connect my points because I want all the numbers between the points too. So my line's just going to start at 0, 0 and go up through all my ordered pairs. Just like this. I want to go ahead and put an arrow on my line to show that that line is just going to keep increasing and increasing and increasing. Because the more bars I eat, the more calories I have consumed. I do not want to put an arrow down here, however. I don't want to do that because I cannot eat a negative amount of bars. I can only eat 0 bars, or I could eat more than 0. So this is what my line would look like. I have now graphed my situation, my function from the example. So hopefully that makes sense. That would be a continuous set of data right there. The previous one was a discrete set of data. This would be a continuous set of data. Here's our assignment for today. Page 120 through 121. Numbers 27 through 36 all. That's not a whole lot. This will be due tomorrow. On Canvas. So you'll have some time to work on it tomorrow on your remote day tomorrow. I'm also planning on giving you guys a quiz tomorrow on Canvas, so make sure you're looking out for that. So you have this to work on, and you'll have your quiz to work on tomorrow. If y'all have any questions, please let me know, and I'll try to get them answered as soon as possible. Hope you guys have a great day and stay warm with this cold weather.